Hello, my name is Juan Soto and I'm going to make a presentation of my master thesis, which belongs to the field of process system engineering. I have tried to summarize the unifying thread that gives support to the whole work in the three following aphorisms. The universe is nothing more than a set of systems that interact with their inputs and outputs. The complex behavior of the universe can be explained by a large number of interactions of nonlinear but simple systems, and force oscillations is one of the methods in which nonlinear chemical systems can exhibit complex behavior, which means that the magnitude and shape of the outputs are modified. The research problem consists in the study of the effect of input oscillations in the solvent structure of metals. This is relevant given the growing interest that oscillations have in chemical engineering, since this type of perturbance allows the possibility to overcome the steady-state performance of nonlinear processes. This is the case of solvent extraction, that is one of the three fundamental unit operations in hydrometallurgical plants, and that supposes a novelty, since till now these kind of oscillations have been only studied in chemical reactors. Regarding the methodology, it consists of a first theoretical part where the mathematical model is elaborated, and a second experimental one through simulation. Results are discussed by comparing the time average value of the output for the steady state and the dynamic oscillatory modes to verify if an improvement is achieved. The thesis has two general objectives of theoretical character that try to show the possibilities opened by modern computational tools. Firstly, by using new object-oriented languages for simulating complex dynamic models, and a second one that tries to find a general and robust method to study the effect of oscillations that improve previous analytical ones. There is also a specific objective of experimental character that consists in evaluating the rate of improvement that is achieved through the oscillations in this process. In the state of the art, the theoretical and practical foundations required to solve the research problem are established. In general, the behavioral system can be predetermined in the case of stable and unstable systems, since they tend to an equilibrium point or disintegration, or indeterminate in the case of complex systems, because they tend to a configuration of equilibrium points known as attractor. In nonlinear chemical systems, the complex behavior related to oscillations can arise spontaneously or by the forced introduction of the same. The necessary but not sufficient condition for complex behavior to arise is nonlinearity. A system is nonlinear when the principle of scaling, or the superposition of inputs and outputs, is not always met. The effect of the oscillation is determined by the mathematical implication of the correlation of the model. The two options for studying the effect of oscillations are the classic analytical methods that are complex, particular, and not completely reliable, and the numerical ones, in which the use of new computational tools opens up the possibility of obtaining efficient and robust solutions for all types of models. In this table, some examples of these methods are collected. On the other hand, in the framework of Bertalanffy's general system theory, a conceptualization of the fundamental notions for the thesis has been carried out, such as the term of unit operation, model, and simulation. In this conceptualization, a system is characterized by a composition, an environment, a structure, and a mechanism. Therefore, unit operations are nothing more than process-divided technosystems that transform the inputs into products with emergent properties, being this the main objective of the chemical industry. Finally, the process considered corresponds to solvent extraction, which consists of the combination of two unit operations. In the first one, that is carried out in a mixer tank, the process consists in the mass transfer controlled by an ion exchange reaction of metal ions from the aqueous phase to the organic one. In the second one, The process, that in this case is physical, is the separation of both phases by gravity inside a set line. Since the oscillations can only have an effect of the process of the first unit operation, in this thesis the second unit operation will not be considered. The mathematical model of the adopted solution, that correlates the inputs with the outputs, has been elaborated using conservation laws and the corresponding quantitative and auxiliary correlations. The criterion that has been followed for the assumptions is not to match the effect of oscillations on the system, obviating or simplifying the secondary aspects. The two most relevant assumptions are perfect mixer and fast kinetics of mass transfer. Consequently, the mathematical correlations of the model for the single component case configure the following nonlinear differential hierarchic system. These three auxiliary correlations determine outlet flow rates. Volumes are calculated applying volumetric balance between the inlet and the outlet. Metal concentrations are obtained applying mole balances to each phase. The thermodynamic model consists of the law of mass action of the reaction that gives the nonlinear character of the system, two mole balances, and a charge balance. The driving force for the reaction is the chemical potential gradient. Finally, the mass transfer is based on Fick's law, being in this case the concentration gradient the driving force. For the multi-component case, the same correlations are applied for the second metal. In relation to one of the general objectives of the thesis, the code is implemented in the novel Simescape object-oriented language, whose characteristics suppose that the code of the model is practically equal to the mathematical formulation of the same, composed of inputs, outputs, parameters, and equations. In these modeling languages, it is not necessary to incorporate the resolution algorithm into the code, this being configured through the graphical interface. It also allows to solve in general any differential hierarchy system for the simulation, design, and control modes. This is the countercurrent cascade flowsheet and Simescape of the process, corresponding to the previous code. For the simulation, the configuration can be done flexibly through the user interface. To study the effect of the oscillations, which is a specific objective of the investigation, AQs and organic flow rates are configured as sinusoidal inputs, keeping the rest of the inputs constant. In relation to the second general objective, corresponding to a method to study the effect of oscillations, the work provides the novelty of solving the key problem of determining the optimal amplitude and frequency parameter values of the inputs to oscillate by optimizing the results of global sensitivity analysis, that is to say, the study of the degree to which the outputs are affected as the parameters are modified. The methods allow to obtain these values through a probabilistic sampling with Monte Carlo simulations that explore the space corresponding to the parameters and outputs to be optimized. The approach adopted for the experimental design and the discussion of the results is based on the comparison of the data obtained through simulation and global sensitivity analysis between the steady state and the dynamic oscillatory modes of operation. These data to be compared are the optimal values of the objective functions, which for the single component case correspond to those that minimize concentration of metal in the waste stream, and in the multi-component case to the values that maximize productivity and purity. Logically, the time interval of the transitory part is ignored, since only the final results of the process are of interest. For the experimentation by process simulation, values on a standard range of variables and parameters taken from the literature review has been assigned. Obviously, the ratio of amplitude and frequency are limited by the condition that there are no negative values of the flows, and by the technical feasibility of the swiftness of the oscillations. The results of the single component case are shown in this plot of the objective function with respect to time. in which the horizontal yellow line corresponds to the steady-state case and the red one to the average value of the oscillation of the dynamic case. It can be seen that there is a minimization of the cost function from 12.94 in the steady-state mode to a value of 9.93 in the dynamic periodic mode. This means a reduction of 23% in the amount of metal lost. For the multi-component case, it must be taken into account that the two purity and productivity objective functions cannot be optimized simultaneously, which implies that there is no optimal point of operation. What can be obtained is a series of points that, when plotting, give the curve that represents the dependence between the two objective functions. In the thesis, 4 steady-state operation points have been considered, to which correspond a point cloud obtained by global sensitivity analysis. All clouds have the same number of points or sample size, but different degree of dispersion. The graph shows that in this case there is no improvement of the process, regardless of the objective functions to be prioritized, since the point clouds are below the curve of the steady-state mode. Regarding the general objective, the work shows the feasibility and suitability of the object-oriented simulation methodology to address the modeling and simulation of real chemical engineering problems. This requires simultaneous solution of differential algebraic systems, such as the case treated in this thesis. It is also verified that global sensibility analysis is a general method that allows to study in a practical way the effect of forces oscillation of nonlinear chemical systems. This method, unlike the analytical ones, is applicable regardless of the number of inputs to oscillate and the complexity of the mathematical model. Additionally, this method also achieves greater reliability and results through the operating range. On the other hand, regarding the specific objective, in the single component instruction, with application of forced oscillation, it is achieved a significant reduction of about 25% in the amount of metal not recovered with respect to the steady-state case. However, this improvement is only possible with amplitudes close to its maximum admissible value, which will imply cost increases due to oversizing of the equipment. Therefore, in general, it is more convenient to achieve the same improvement but slightly increasing the organic flow rate. In the multi-component case, it is not possible to achieve even a particular improvement of the process for a specific point. Hypothetically, it is considered that this could be explained by the similar nonlinearity, since both metals are bivalent. This causes coincidences in the effects of the oscillation of both metals, and not opposed as required to maximize the product and minimize the impurities. From the study I have made of the research published in this field to date, it follows that it has many problems of chemical engineering. The state of the art is at an empirical level in which at most the effects of oscillations are attributed to the mathematical implication of the nonlinearity of the model correlations. This assumes that we find the complex situation of the so-called inverse problems, in which the causes must be inferred from the effects. In fact, what we are certain about is that oscillations perturbate thermodynamical equilibrium, producing an alternating series of equilibrium states to which, as we know, corresponds to a minimum energy and a maximum entropy. In short, the perturbation causes a change in the time average value of the concentrations. This problem is reflected in engineering in the need of using black box models with the corresponding nonlinear correlations between the inputs and the outputs, as is the case with this thesis. Logically, the foundation of this field will require the identification and quantification of the interaction mechanisms at the intra- and the intermolecular level responsible for the effects of the oscillations. This is nowadays an open, highly complex issue that is in an initial stage and corresponds to a level basic or fundamental research. With this, I have finished my presentation. I hope you will find of interest.